All right, so I guess today we'll finish talking about optimization and the technique of Lagrange multipliers. And so there's three types of optimization problems that we're going to be doing in this course. So essentially, the two that we talked about yesterday were this two-variable unconstrained problem. So this was week 6. Lecture 1. And so that was when our domain for x and y was a two-dimensional region in the xy plane. So I guess the example we did was like a triangle. I think we also did a quarter disk yesterday. But it's all about the domain of our x and y. And we called this unconstrained because the idea was that if you pick a point that you care about all other nearby points, not just points on a curve, which was this situation up here, where we were still optimizing f of x, y, but the x's and y's were only allowed to live on a curve g of xy equals k. So this is g of xy equals k. And so yeah, the only points that we care about are on that curve. We don't care about all other nearby points. And so we called that constrained. And so we approached these problems differently. So we did this one first down here, this one, the unconstrained. And so that was a two-step process that was pretty similar to what you had in Calc 1, where the first step is you find your critical points, which in this case is when your gradient is the 0 vector, which is just another way of saying both partial derivatives are equal to 0. But then in Calc 1, you check the endpoints, the boundary, which in Calc 1, you didn't need calculus on the boundary because it was just two endpoints. Big deal. F of A, F of B, takes 2 seconds to plug those in and compare the values with your critical points. But in this situation, when you go to your step 2, you don't just have finitely many points, you have basically infinitely many points that live on the boundary of your two-dimensional regions D. And so basically you need Calc 1 on this boundary to tell you what are the important points. And so yesterday we looked up, basically you describe the pieces of the boundary in terms of one variable, and so you get Calc 1 problems since there's only one variable involved. Okay, and then we saw a different way. If your curve that you're interested in optimizing on is a level curve of the form g of xy equals k, then we could do something called Lagrange multipliers, and that's what we ended yesterday's lecture with. So I guess to start off today, I'll tell you that, okay, the third type of optimization or problem that we'll do is a function of 3 variables, f of x, y, z, but it's still going to be constrained in that we're going to be considering points x, y, z that live on the surface g of x, y, z equals k. That you get a level curve for g of x, y equals k, but you get a level surface for g of x, y, z equals k. Okay, and so we'll have Lagrange multipliers for that. So I guess this is a quick review of yesterday's, what we did for Lagrange multipliers. These first two equations were basically saying that grad f and grad g are parallel vectors. And so parallel vectors means that one is a scalar multiple of the other. So we have this grad f is lambda times grad g. And then we also remember that we are enforcing that g of xy has to be k. So that's our third equation for our system. And so we solve that system, plug back into f to find the greatest and least. That's what we did yesterday. So it turns out for 3 variable, 1 constraint optimization, you basically do the same thing. The picture is a little bit harder to justify. So yesterday we looked at the contour map of f and overlaid the level curve g equals k, and we convinced ourselves that points of interest are going to be when those gradient vectors are parallel. It's a little bit harder to do for this 3-variable case because this contour map of f of x, y, z is going to be a bunch of surfaces, and it's just pretty tricky to draw. But instead, you could just take my word for it that for this situation, we're still interested in these vectors being parallel. And so we get this same kind of system, except now since these are these functions of x, y, and z there's 3 variables, the gradient vectors are 3-dimensional vectors. So this single vector equation breaks up into 3, I didn't mean to circle the bottom one, but 3 scalar equations. And then just like before, we also have to have g equals k so that we have the same number of variables as equations, because the idea is that we have x, y, and z floating around, but now that we've introduced this constant of proportionality between the gradient vectors, lambda, that's a 4th variable, and so we have to close the system and have g equals k as well. Okay, so we'll do an example of that in a moment, but what I wanted to start showing you is that sometimes you can convert between different types of problems. So yeah, we started yesterday talking about constrained versus unconstrained, and it turns out that if the algebra is convenient, you can take like a n variable 1 constraint to an n minus 1 variable unconstrained. And so the types that we'll look at for particular values of n are going to be, sometimes you could go 2-variable constrained to 1-variable unconstrained, or 3-variable 1 constraint to 2-variable unconstrained. So maybe, I know a lot of this is going to be pretty tricky your first time viewing it. Maybe come back to, maybe I'll take us back to this slide. But yeah, rewind the video after you've seen all these examples that we're talking about today. So this idea of converting between different types of problems is actually an idea that I think most of you are familiar with if you took the standard sort of Calc 1 course. So one of the problems you did in Calc 1 was maybe something like this. So you're building a fenced rectangular pasture against a barn. So okay, we got our barn over here, or I guess the wall of the barn. And we want to find the maximum area we can enclose if we have 20 feet of fence. And so the idea here is you would start drawing your variables. So, okay, let's say our rectangle fence area has dimensions x and y. And so we want to maximize area. So area, of course, of this rectangle is just going to be xy, right? And then the idea is that in Calc 1, you didn't know how to do derivatives involving multiple independent variables. So you had to somehow reduce this 2-variable problem to a 1-variable problem. And what you did was you used the perimeter constraint to do this. So we know that perimeter, which because we're using the side of the barn, we don't need to use any fence over there. We have that the perimeter is 2x plus y, and if we have 20 feet of fence to use, that's going to have to be 20. So this perimeter constraint tells us that y is 20 minus 2x, and so therefore the Calc 1 way is to solve this 1-variable unconstrained problem, which was maximize a of x, which is x times 20 minus 2x, for, I guess the domain for this would be x between 0 and 10, right? If I'm stuck with 20 feet of fence, I can make it a lot longer, but I only have 20 feet of fence to work with, so as y goes to 0, x would approach 10 for this perimeter constraint. Okay, and so the reason why it's unconstrained is that it's only a 1-variable problem, and our domain is 1-dimensional. It's this interval on the number line 0 to 6, or 0 to 10, sorry. And so, yeah. And what you did in Calc 1, you did a prime of x, which would be 20 minus 4x, I guess, right? Because 20x minus 2x squared has derivative 20 minus 4x. You set that equal to 0, so you get x equals 5, and so on and so forth to justify that that's in fact, the maximum. But that's the Calc 1 way. And so what I want to show you is that there's a Calc 3 way. And so the Calc 3 way is to do this same thing, but leave the perimeter as a constraint and use Lagrange multipliers. So the Calc 3 problem would be 2 variable, 1 constraint, and it would be find the max of a of xy, which is xy, subject to 2x plus y equals 20. And so this is the type of thing we did yesterday with Lagrange multipliers. You would set up gradient of A, because we're using A instead of F, is lambda gradient of G, where G of xy is that 2x plus y. So, okay, let's set that up and make sure that we get the same answer. But yeah, so after more work, you'd say that, okay, this is 5, this is 5, this is 10, is the maximum area that we can enclose. Okay, so anyway, this Lagrange setup then, the x partial of A is y, the y partial of A is x, is lambda times, well, the x partial of G is 2, and the y partial of G is 1, and then I have my constraint, 2x plus y equals 20. And so I guess I could do the same kind of thing that I did yesterday and see that lambda is x from the second equation. The first equation tells me that lambda is y over 2, so therefore x has to be y over 2. And so at that stage, you could plug that in to equation 3, which would tell you that, well, y plus y is 20, so y is 10. And then plugging that back in, you'd get then that x is 5. And so, of course, you get the same answer as you would have in Calc 1. And so hopefully that shows you a little bit more concretely the equivalence of these two problems. And so, honestly, Lagrange multipliers is more flexible. Essentially, the reason it worked out nicely enough for the Calc 1 method was that this wasn't so complicated. You could easily solve for y. We've talked several times in this course about how sometimes things are impossible to solve algebraically. So there could be equations that are just too darn complicated to solve for y in terms of x. And so that would be a situation where you'd be forced to do it the Calc 3 way. But I think it's important to understand that, yeah, there's different ways you could tackle different types of problems. And it's all about keeping straight. When you're solving unconstrained, you're setting derivatives to 0. Whereas if you're solving constrained, then you're doing parallel gradients and using the technique of Lagrange multipliers. So as long as you don't mix up the two methods you see, then you get the same answer, of course. So your choice for something like that. And so now I want to show you the other situation that we talked about, that sometimes you could do 3 variable 1 constraint and convert that to 2 variable constrained. So let's revisit a problem that we did yesterday, which was minimizing the amount of cardboard needed to construct an open top box with volume 500 cubic inches. So What we did yesterday was we had our no top x, y, z. So yesterday's approach, well, maybe I'll just, the setup is the same for both to start. So anyway, we want to maximize, or sorry, we want to minimize cardboard. So minimize surface area, which is xy plus 2yz plus 2xz, since we're missing our top, subject to the volume, which is xyz, being 500. So yesterday, which was the two variable unconstrained approach, was to minimize, we could call it f of xy equals xy plus 1,000 over x plus 1,000 over y, because we were able to solve for z in the volume equation and replace that in the surface area equation to get surface area only in terms of x, y, and z. And so once we've gotten rid of z, the domain for x and y is just the entire first quadrant. So that's unconstrained. It's a two-dimensional domain for a two-variable function. And so we solved the system fx equals 0, fy equals 0, and after a bunch of work, well, not that much work, I think we got x was 10, y is 10, and z is 5, I think is what we got. So 300 inches squared was our minimum. And so instead today, I want to show you how to treat this as a three-variable one constraint. So in this case, we'll want to minimize, I'll use a capital F just because it's a different function, so we're not confused, but leave surface area in terms of x, y, and z, but then leave the volume constraint as a constraint. So the Lagrange phrasing for this would be minimize xy plus 2yz plus 2xz subject to the constraint xyz equals 500. And so this is a Lagrange situation. So we'll do grad f is lambda grad g, and g equals k. So we get the four equations. Well, so the x partial of f is y plus 2z. The y partial of f is x plus 2z. And then the z partial of f is 2y plus 2x. And those are equal to lambda times the respective derivatives of g. So the x partial of g is yz, the y partial of g is xz, and the z partial of g is xy. And then again, I highly recommend not forgetting to include your constraint here, which functions as our fourth equation, which we need because we have x, y, z, lambda, four variables, so we need four equations. Okay. And so I guess there's a few things you could do here. I guess, yeah, so I guess the first thing to notice is that Luckily enough, in this problem, none of these dimensions can be 0, right? Because if any of x, y, or z are 0, there's no possible way the volume will be 500. Which means you're allowed to freely divide or do whatever you want. So you could do the same kind of thing that we did before and solve for lambda. I'll show you something a little bit different that happens that occasionally can be helpful for certain problems like this. But notice if I do x times equation 1, I get xy plus 2xz is lambda xyz. If I do y times equation 2, I get xy plus 2yz equals lambda xyz. And if I do z times equation 3, I get 2yz plus 2xz equals lambda xyz. So the reason I decided to do that was that I noticed that the right-hand side was almost the same, except the first equation was missing x, the second was missing y, the third one was missing z. And so I don't know, this works out. So basically now I use the fact that these two are equal to get that xy plus 2xz equals xy plus 2yz. So xy cancels. The fact that z can't be 0 allows me to say that x equals y. All right, so I'll show you an example in a few minutes where you want to be careful dividing by a variable, but we've already decided for this problem that z can't be 0, so that x has to be y. Okay, and so then if I do equations 2 and 3, I would get that xy plus 2yz equals 2yz plus 2xz. Well, the 2yz's cancel out, so I get xy equals 2xz, but I already had that x is y, so this is x squared equals 2xz, which again, using the fact that z can't be 0, tells me that x has to be 2z. So yeah, again, we're allowed to divide by whatever we want. Nothing can be 0, neither x nor y nor z. Oh yeah, sorry, so technically that's not this. I'm dividing by x. So it's safe to divide by x to get that x is 2z. Okay, and so notice I'm staying organized, and every time I'm getting something useful like x equals y and x equals 2z, I'm boxing that because at this stage I'm going to do everything in terms of x and see where that leads me. Or whatever, we could do it in terms of z. So I've used equations 1, 2, and 3. I haven't used equation 4 yet. So equation 4 says that xyz is 500. But, well, y is x, and z is x over 2. So I get x cubed equals 1,000, so x is 10. And then I look around, well, y is x, so y is 10. And z is x over 2, so z is 5. And so I get yeah, 300 inches squared of cardboard was the answer there. Okay, and so yeah, that's the same thing we got before. Again, I'm sort of skipping over the proving that this is in fact the minimum amount. Like I mentioned yesterday, for multivariable functions, that's a trickier issue than it was in Calc 1. And so we don't really want to get into that. But you can assume that if I'm only asking for a minimum and you only get one solution, that ends up being the answer, that I'm not going to try and trick you out here. That we mentioned yesterday, this problem has no maximum. And so I'm not going to be tricky and ask you for the maximum when there isn't one. So anyway, it's up to you how you want to try some of these problems. You can get rid of one of the variables, do gradient equals 0, or you could keep all the variables and do Lagrange multipliers. So I don't think I added any homework. I'm pretty sure these homework problems are accurate, but essentially you'll notice when you're doing homework 6 that there's certain problems that seem to appear twice. And so I believe that happens 3 times. And so the idea is that at first they're showing up in 14.7 and afterwards they're showing up in 14.8. And so the idea is that the first time you're supposed to do it what we did yesterday, where you reduce it to a 2-variable question and set the 2 partial derivatives equal to 0. Whereas when you go and redo it, you should do it using Lagrange multipliers. Obviously, we're not going to know how you do this, but I think that this is going to be key to really understanding what's going on. And so it's up to you. I think I prefer the Lagrange multiplier situation because it's more flexible. You don't have to have a nice, simple algebraic equation that you could solve for one of the variables. But it's up to you. Decide which one you're going to use. And make sure, I would recommend practicing both methods so then you could decide for yourself which one you prefer. Okay. So the next idea is how you might have been thinking a few minutes ago that qualitatively, this Calc 1 boundary is kind of like a curve. So you could have some regions where instead of like a triangle, maybe the boundary is like a circle like this. I know yesterday we did another one where the boundary was a line segment and piece of a circle. And so the idea is that whenever your region has corners, which require the boundary then to have a piecewise definition, you're going to want to do what we did yesterday and set up those Calc 1 problems on the boundary. But if your boundary instead doesn't have corners, then it's probably your best bet to use Lagrange multipliers on your boundary. So let me show you how that could work. So I think that's what this slide explains. Yeah, so we looked at triangle and quarter disk yesterday. The boundary had corners, and we set up different Calc 1 problems. If our region is given by a nice level curve, then you can use Lagrange multipliers in the boundary step. So this question here looks a lot like what we did a couple of examples of yesterday. So let's draw our region and think about it. So our domain is x squared plus y squared less than or equal to 9. And so our first step is grad f equal to 0 inside. So we need both partial derivatives to be 0. 6y equals 0, so we get the critical point 1, 0. Which, okay, I guess this is radius 3 circle, maybe somewhere there. Okay, and so the next step is the boundary, x squared plus y squared equals 9. So again, when we have this inequality here, this is a disk, and when it's an equals, it's a circle. So we've taken the boundary of the disk and we get a circle. And so that's what, you could do something yesterday. You'd have to break it into 2 pieces, or you could parameterize using t and do 3 cosine t, 3 sine t, and to get f in terms of t. So it's up to you, but if we tie together what we've been talking about more recently, the Lagrange multipliers, that's when you would set up gradient f, so 4x minus 4, 6y, equals lambda times gradient g. So this is our, I guess more precisely, yeah, whatever, it's the same thing. That's your g of xy. And so one mistake I've seen people do in the past is try to use Lagrange for the whole thing and put an inequality here. It's actually nonsense. So you really don't want to do that. I mean, you're not going to get this 1, 0 point if you do something like that. And in addition, yeah, I mean, you can kind of get pieces of the correct answer, but you're either ignoring something or getting lucky. I really just recommend thinking about this as a two-step process. That step 1, your gradient of f is the 0 vector. Step 2, gradient of f is lambda gradient g, and g equals k. That Lagrange is actually nonsense with an inequality. So never do Lagrange with an inequality. Only ever do equals. And it makes sense because we're done. You know, the first step of the extreme value theorem is, okay, if the extreme values are anywhere on the inside, it would be at a critical point or the boundary. And so on the boundary, it becomes an equals. And so this really is what we want to be dealing with. Okay. And so anyway, let's solve this system. And so equation 2 looks simple. And so to tie it back into what we were talking about last week, you want to be careful that you factor and not cancel things. So a lot of you might be looking at equation 2 and saying, yeah, lambda has to be 3. Well, y could be 0. So instead of crossing out a y, I instead can create a 0 and get that 2y times 3 minus lambda equals 0, which means that y is 0 or lambda is 3. And so this is sort of what I showed you guys to do last week, that when you're dealing with systems of equations, factor, don't cancel, and stay organized. So if y is 0, I can immediately go to equation 3 to get that x is plus or minus 3. And then if lambda is 3, I should take that to equation 1 to get that 4x minus 4 is 6x. So that what, 2x is negative 4, so x is negative 2. And then the third equation tells me that 4 plus y squared equals 9, so y is plus or minus square root of 5. And yeah, so anyway, I get the point negative 2 root 5, negative 2 minus root 5. And then here, I can quit. Oh, and I'm doing it backwards. It's x is plus or minus 3. So 3, 0, minus 3, 0. And so you might be wondering, okay, why did I, once I got y is 0, I went straight to equation 3. I didn't ever use equation 1. Is that okay? And the answer is yes, because technically, you know, solutions are triples, x, y, lambda. This is a system of equations for 3 variables, x, y, lambda. And so sometimes you'll find the lambda value on the way. So for those two solutions, lambda equals 3 was an intermediate step. But then for this, if you go back to equation 1, you could figure out the lambda value. So if x is 3 and y is 0, I would have 12 minus 4 equals 6 lambda. So after you substitute it in, it turns out that lambda is 4/3 for this. And that, what, negative 16, so 16/6, which is what, 8/3? Lambda equals 8/3, I believe, is the solution there. But these actual lambda values, we don't really need them because the last step here is to do f of 1, 0, our critical point on the inside. Don't forget about that. But then we also need to do f of 3, 0, f of negative 3, 0. And then it turns out that these 2 points have the same f value. Okay, so let's, what is this? 2x squared plus 3y squared. Let me zoom out. So 1, 0 looks like it's what? 2 minus 4 plus 2, which is 0. F of 3, 0 is what? 18 minus 12 is 6 plus 2 is 8. F of negative 3, 0 is 18 plus 12 is 30 plus 2 is 32. And then, okay, so 8 plus 15 is 23, plus 8 is 31, okay, 33. I think I'm doing this right. This is just the tedious, kind of boring finishing step. So what, 8 plus 15 is 23, plus 8 is 30, okay. So it looks like then that this is our absolute max, and this is our absolute min. And so notice, we didn't really care about this. So if it happens that you are solving and you're able to get your x and your y values before you get your lambda value, there's no sense in worrying about what that lambda is. It's important that there is one, but it's not important what it actually is because we didn't need to know lambda for this final step. So if you get a y, you can immediately go to the third equation and get your x's. Other times, lambda values will be an intermediate step. So. And it very well could have been that one of these was the actual answer. So your complete answer to this, you have to check these 5. But that's it. So when you find yourself with a unconstrained problem, whether or not you use what we talked about yesterday or Lagrange depends on if your boundary curve has corners or not. And so I would use Lagrange multipliers if your domain is some sort of disk where the region, the boundary of the disk, x squared plus y squared less than or equal to 9, becomes the circle x squared plus y squared equals 9. That's going to be well suited for Lagrange multipliers. Okay. And so anyway, then, that's pretty much about it. The last thing I wanted to talk about today was just the cool idea that Lagrange multipliers can be very flexible and apply to any number of variables, any number of constraints. You basically set it up in the same kind of way. So I'll show you the pattern for 3 variable 2 constraints. So if I want to max or minimize f of x, y, z, subject to one constraint g equals k and the other h equals l, then you would set up and solve this system of equations. And so the idea is that each constraint gives you a term on this right-hand side. And each of those constraints causes you to introduce one Lagrange multiplier. And so, yeah, this technique we've been using was Lagrange multipliers. Most of the example, I guess all the examples we'll be doing in this class for your quizzes and exams will only have one Lagrange multiplier. But if you have multiple constraints, you get multiple Lagrange multipliers. And so in the language of Math 220, essentially what we need is that the whole technique of Lagrange multipliers boils down to the gradient of the function you're trying to optimize has to be a linear combination of the gradients of the constraint functions. And so linear combination means something like this, that vector A is some scalar times vector B plus some other scalar times vector C. And so when you only have two here, then the concept of linear combination for one to be a linear combination of one is just to be a parallel vector. But when you have multiple constraints, you get this linear combination going on. If you count your variables, you have x, y, z floating around, but now you have the two new variables floating around. So wait, you say, oh, this is 3 equations, 5 variables. What am I going to do? I'm going to be sure to include the constraint equations as well. So don't worry about this for quiz or exam. I put on, I think the very last problem on the homework is like this. And so it's not this problem, but let's do one that's similar. I think on the homework it's asking for points closest and farthest from the origin, and you kind of have to figure out what to do for that. So let's see if we can find the highest and lowest points on the curve of intersection of these two surfaces. So it turns out that this 3-variable, 2-constraint problem, it actually can be converted to a 1-variable unconstrained. The examples I showed you earlier today, when you have 1 constraint, you could shave that off to reduce the number of variables by 1. It turns out that if you have multiple constraints and that they're somehow compatible with each other, you could knock off 1 variable per constraint that you knock off. So like one way to interpret this question is to, so I'll put this as a 1. If you wanted to approach it like this, you could do, we could find R of t for the curve of intersection. That's something that we did back in chapter 13. Remember, we had 2 surfaces and we asked ourselves, we have 2 surfaces and we were asking ourselves, okay, well, how do we get an equation for the curve of intersection? And so this one's going to be a little bit trickier than the one we did. And okay, let me see if I can remember how to do this real quick. So find R of t for the curve of intersection, then to find the highest and lowest points, you're going to want to maximize, minimize z of t. So remember, R of t is going to be x of t, y of t, z of t. And we do that there. So you'll notice, though, that this isn't like the examples that we did back in chapter 13. Usually we had some kind of circular cylinder or parabolic cylinder going on as one of our surfaces. And so that gave us a nice way to get this thing. So let me see if I can. Oh, okay. So if we do this trick where we use like polar coordinates, RT for x and y. So if I said like x is r cosine t, y is r sine t, I could figure out that the cone equation, the second equation, becomes z is r. And then the plane ends up being 4r cosine t minus 3r sine t plus 8z equals 5. But if I plug the cone equation into the plane equation, I get that 4z cosine t minus 3z sine t plus 8z equals 5. So I could solve for z of t is 5 over 4 cosine t minus 3 sine t plus 8. And this would be the z of t that I would be interested in doing. So I guess putting it all together, I'd have to then substitute in, it would be a big mess, that r of t is r cosine t. So r is z, so 5 cosine t over 4 cosine t minus 3 sine t plus 8, comma, z sine t, so 5 sine t over 4 cosine t minus 3 sine t plus 8, comma, z, so this. Anyway, this is pretty tricky. I had to think about it for a moment. But for those of you who got lost, it, just sort of couldn't follow what I was doing right here, it goes to show you that this find r of t for the curve of intersection, it's is harder than what we did in chapter 13. And also, it could be impossible. So this whole theme of being able to occasionally avoid Lagrange multipliers relies on the fact that you can algebraically manipulate these. And so algebra could be hard or impossible. I would say this one's a little bit harder. But if you're trying to treat this as a one variable unconstrained, you would set z prime of t equal to 0 and kind of go from there. So anyway, what I'm going to show you is that this way of thinking about it in terms of Lagrange multipliers, two constraints, lets you deal with this without having to fool around with this algebra. So leaving it as 3 variable, 2 constraint, we want to maximize, minimize. It's asking for the highest and lowest points on the curve, so you have to ask yourself and think, what does it mean for a point on a curve to be the highest or lowest? Well, that means that the function that we're trying to maximize and minimize is the z coordinate, right? What is the highest point? It's the point with the maximum z. What is the lowest point? Minimum z. If you want to do like leftmost and rightmost, depending on your perspective, that could be x or y or something like that. But the function that you have to optimize is z, right? Find the highest and lowest points. And then subject to 4x minus 3y plus 8z equals 5, and x squared plus y squared equals z squared. This would be your first constraint, g of x, y, z equals k. And then this, I guess, well, let me just rewrite this cone equation as x squared minus, or plus y squared minus z squared equals 0. So that's our h of x, y, z. So that our big system of equations becomes grad f, which is 0, 0, 1, is lambda times grad g plus mu times grad h, and then g of x, y, z equals 5 and h of x, y, z equals 0. And so you kind of go from there. It's a big mess. We're not going to make you solve a 5x5 on a quiz or an exam, but this would be what you would then ask your computer for help for. This one you can actually do. But I mentioned yesterday when you're towards the end of class when somebody asked about multiple constraints, that this method could be extended to any kind of situation. Just imagine you're running a company and you're trying to maximize profit. Well, that's something huge. And who knows how many variables and how many constraints, how many rules you have to follow. And so this whole power of optimizing, that's sort of, in my opinion, one of the most important applications of calculus. But yeah, 3 variable, 2 constraint. Give that a shot on the homework. If you get stuck, shout out for help. But thought it would be fun to look at this. And like we saw earlier today, there's always different ways you can approach it. That if your equations are tractable and you can eliminate variables, and turns out that this is a Calc 1 problem in disguise, right? Once you've figured out the parameterization R of t for this curve of intersection, it ends up being a Calc 1 problem. What? Set z prime of t equals 0? But if you don't see that trick and you just want to leave x, y, and z instead of getting them all in terms of t, then you could set up this 5x5 system. So there's always this interplay that you could have this big system that's relatively simple, or a smaller system, in this case a single equation, that's kind of a big mess, right? Take the derivative of this, you're gonna get something nasty that's not too much fun to deal with. But anyway, don't worry about that for quiz or test. Focus mainly on these 3 that I started off today about 2 variables, constrained or unconstrained, and then 3 variable constrained. So anyway, it's about all I had planned for today. Any questions? Well, no questions. I will see you all later. Maybe not the 231 people, but yeah, good luck on the final exam, and enjoy the rest of your summer if that's the case. Otherwise, 230 people, haven't seen the last of me. Anyway, have a good day, good week.